Hi, this discussion on electromagnetic waves is in line with the BSc Physics syllabus of the University of Calicut. This is the outline of the syllabus, and in this course, we shall try to understand the wave equation and its basic properties, boundary conditions under reflection and transmission in the first part. In the later part of the syllabus, we shall focus on electromagnetic waves. We shall begin our discussion by defining a wave. A wave is a disturbance of a continuous medium that could propagate with a fixed shape at a constant velocity. What you see here is a waveform having an arbitrary shape. So this is the shape of the wave at time t equal to 0. If it is assumed to be having a velocity v, in time t, it would have moved a distance vt, and now the position of the wave will be here. All waves except electromagnetic waves, on which we will learn a little bit later, needs a material medium for their propagation. If the media is characterized by a finite absorption coefficient, then the amplitude of the wave will diminish in size as the wave propagates through the media. And now, if the medium is dispersive, different frequencies will travel at different speeds. In 2 or 3 dimensions, as a wave spreads out, its amplitude will eventually decrease. A special kind of wave is a standing wave, which is actually a superposition of a forward and backward moving waves. A standing wave does not propagate at all. So these points gives us an idea on the fundamentals of wave motion. Our next attempt is to find a mathematical representation of wave propagation. Let us consider a wave that is traveling in the forward direction. The wave that we are considering has an arbitrary shape as shown, and it is mathematically defined to be f z, 0. Here z is the direction of propagation of the wave and f is its amplitude. This 0 inside the bracket represents time. So the wave is defined at a point z and at a time t equal to 0. Let us consider a point like this on that wave. If we assume that the wave has a finite velocity v and it is moving in the positive z direction, after time t, it would have covered a distance vt, and now the position of the wave will be here. When a finite time t has been elapsed, the wave function is mathematically represented by f z, t. That is, the point that we have considered in the wave has traveled a distance vt in time t. Now let us assume that at t equal to 0, the shape of the wave is defined to be gz, and that is equivalent to f of z, 0. Now, what would be the shape of the wave at time t, that is at this particular point? Let us take the amplitude of the point to be f. Now, if we consider a point z minus vt, we can find that the amplitude of the wave is the same and its value is f. And from this observation, we can write f of zt, this is equal to f of z minus vt defined at time t equal to 0, and mathematically this can be written as a function g z minus vt. This equation means that f zt depends on z and t in a very special combination z minus vt. If we consider two constants a and b with appropriate units, we can frame the wave equation mathematically as f1 zt equal to a e raised to minus b z minus vt the whole square, or like f2 z comma t equal to a sine b z minus vt, or like f3 zt, this is equal to a over b z minus vt the whole square plus 1. You can see that in all these equations we have this argument z minus vt. And these are some of the possible equations for wave motion. Now let us consider equations that are mathematically not possible for wave propagation. An equation of the form f4 z comma t equal to a e raised to minus b b z square plus vt, or f5 zt equal to a sine bz and then cos bvt cube. These are all mathematical forms that are not possible for wave motion. You can see that in the first case z appears as a square, and in the second case vt appears as a cube. We now have understood that when we try to write a mathematical representation for wave motion, what should be the terms that should come inside the representation. To derive the general wave equation, we consider a typical example of a stretched string. The string is fixed at two ends, and let us assume that we apply a force F along this direction. As we plug the string at some point in space, say at z, it moves from its equilibrium position. We shall try to understand the wave motion by drawing the distance versus amplitude of the wave motion. Let us consider a particular portion of the string that has been displaced by the wave motion. We consider two ends, so this end is located at z and this end of the string is located at z plus delta z. The tension at z plus delta z is along a direction tangential to the string, and let us resolve it into horizontal and vertical components. Let us assume that this angle is theta prime. Now the tension at position z is along the tangential direction, and so this is t. And if we resolve this into two components, these are the two components, the vertical and the horizontal component, and this angle is theta. From this figure, we can write the vertical component of the tension that is acting on the string as t sine theta prime at z plus delta z, and at z the tension acting on the string is t sine theta. Therefore, the net transverse force delta F on a segment between z and z plus delta z is given by delta F equal to t sine theta dash minus t sine theta. Let us call that as equation number 1. As you know, theta dash is the angle the string makes with the z direction at point z plus delta z, and theta is the corresponding angle at point z. Now, if the distortion in the string is assumed to be small, theta is small, and in that case, sin theta can be approximated to be tan theta. Therefore, this expression can be rewritten as delta f approximately equal to t times tan theta dash minus tan theta, and this can be written as t multiplied by dou f over dou z at z plus delta z minus dou f divided by dou z at z. So this equation can be written as t multiplied by dou f over dou z at z plus dou square f over dou z square multiplied by delta z. So this is from the fundamental principles of calculus, and the last term is dou f over dou z at z. These two terms get cancelled, and therefore we are left with delta f as equal to t over dou square f over dou z square, then delta z. We shall take this as equation number 2. Now, from Newton's second law, the force is given by mu times delta z multiplied by dou square f over dou t square, where mu is the mass per unit length. We'll take this as equation number 3, and therefore t multiplied by dou square f over dou z square multiplied by delta z, this is equal to mu times delta z, then dou square f over dou t square. From this, we can write dou square f over dou z square as equal to mu over t, then dou square f over dou t square. Evidently, small disturbances on the string satisfy the equation dou square f over dou z square equal to 1 by v square, then dou square f over dou t square. Here v represents the speed of propagation. We'll take this equation as equation number 4. Equation 4 is the classical wave equation. It admits as solutions all functions of the form f zt, this is equal to g of z minus vt. That is, a function that depends on variables z and t in the special combination u equal to z minus vt. And this represents a wave that is moving in the forward direction. A wave traveling in the negative direction could be represented as f zt equal to h of z plus vt. And most of the time, we take the general solution of the wave equation as the sum of a wave that is moving to the right and a wave that is moving to the left. so that we can write the general wave equation as fzt equal to g of z minus vt plus h of z plus vt. We shall now try to understand about sinusoidal waves. A sinusoidal wave is a wave that is represented by a mathematical function having sine or cosine terms. A typical example is f zt equal to a cos k z minus vt. So for this particular wave, the amplitude will be maximum at z equal to 0. If the amplitude is maximum elsewhere, like this case, so this amplitude is maximum at this particular point. Let us take this as delta by k for the time being. And in that case, the mathematical function of this wave has to be rewritten as a cos k z minus vt plus delta. The reason for taking this as delta over k will become evident in a moment. In this expression, a will be known as the amplitude of the wave, and the argument of the cosine function is called the phase. So this term is what we call as the phase of the wave. Delta will be known as the phase constant, and note that any integer multiple of 2 pi added to delta will not change the mathematical function fzt, and the value of delta is between 0 and 2 pi. So this is the graphical representation of the wave that we have just considered. The mathematical function fz is along the y-axis, and the propagation direction of the wave is along the z-axis as shown. A represents the amplitude of the wave, and v is the velocity with which the wave is moving along the positive z direction. As you can see in this figure, the central maximum of the wave is displaced by a distance delta over k. Now the general expression that we wrote for this wave was fzt equal to a times cos k z minus vt plus delta. And the central maxima occurs when the phase is 0. In that case, we can write k times z minus vt plus delta equal to 0, from where we have z equal to vt minus delta over k. Thus, we see that delta over k is the distance by which the central maxima and therefore the entire wave is delayed. And we call k as the wave number. And wave number is related to the wavelength by lambda equal to 2 pi over k. As time passes, the wave train moves to the right with a velocity v. We define the period of oscillation as t equal to 1 over nu, and this is again equal to lambda divided by v. And when we substitute for lambda, we get the period in terms of the wave number as 2 pi over k times v. So in this expression, nu represents the frequency of oscillation. And we know that the wave motion is analogous to uniform circular motion. And therefore, we may define a more convenient unit to the frequency, the angular frequency. Angular frequency represents the number of radians swept out per unit time. And we define angular frequency as omega equal to 2 pi nu, and this is equal to 2 pi times kV divided by 2 pi. These 2 pi get cancelled, and therefore omega is equal to k times v. In terms of omega, a sinusoidal wave may be represented as f zt. This is equal to a times cos k z minus k multiplied by omega t over k plus delta. These two k's get cancelled, resulting in a cos kz minus omega t plus delta. A sinusoidal oscillation traveling in the negative z direction can be represented as fzt equal to a cos kz. Now the sign of omega t has to be positive, because now the wave is traveling in the negative z direction with a velocity negative v. Therefore, the second term has to be plus omega t, and the phase constant has to be reversed. That is, it has to be negative delta. Why should delta become negative? For that, let us consider a wave that is propagating in the negative z direction. And in this case, a delay means a shift to the right. Since the wave at an earlier time is shifted to the right, the delay in delta has to be shown by reversing its sign. If that explanation is not sufficient, let us consider this explanation. So this is a wave that is represented by y equal to cos theta. So this will be pi by 2, and this is pi, and this point is 3 pi by 2. Now let us assume that we give it a delay of pi by 2. So in this case, this will be negative of sine theta, and this wave can be represented as this is pi by 2, this is pi, and this is 3 pi by 2. So this portion of the wave, we can say, has been shifted to the left. That is, in order to show a wave that is propagating along the negative z direction, we have to reverse the sign of the phase constant delta. Now we can write the equation for a wave that is traveling in the negative z direction in a slightly different way. We know that a cosine function is an even function, so that we can write cos of theta as equal to cos of minus theta. Therefore, cos of kz plus omega t minus delta could be written as cos of minus kz plus omega t minus delta. This will be cos of minus kz minus omega t plus delta. Let it be equation number 11. Now we shall compare equation number 11 with equation number 10 that we have previously written. Equation number 10 represents a wave that is propagating in the plus z direction, whereas 11 represents a wave that is propagating in the negative z direction. Therefore, we could simply switch the sign of k to produce a wave with the same amplitude, phase constant, frequency and wavelength to represent a wave that is traveling in the opposite direction. In the discussions that are coming in the preceding sections, we shall reverse the direction of k to represent a wave that is propagating in the negative z direction. Now, instead of using sine or cosine functions, we can write equations with complex notations for wave propagation. We know that the Euler's formula is e raised to I theta equal to cos theta plus I sine theta. The sinusoidal wave in equation 9 therefore can be written as f zt equal to the real part of a e raised to I kz minus omega t plus delta. Thus, we may introduce a complex wave function as f zt. In order to show that it is a complex function, we'll put a tilde like this, and this is equal to a tilde. This also shows that a, the amplitude, is also a complex function, and then e raised to I kz minus omega t, where a with a tilde is a complex quantity, and in this expression the real amplitude a has absorbed the phase constant e raised to I delta. And the actual wave function is the real part of complex f, and this is written as f zt equal to the real part of the complex function f zt. The main advantage of using complex notation is that exponentials are much easier to manipulate than sines and cosines.